Yeah, look into this question. Says that the sample of oleum given is this part. Find the number of moles of NaOH required to completely react with one 178 grams of oleum. Okay, right. We know that NaOH be able to titrate both SO3 as well as H2SO4. What is the reaction type? You know that 2 moles of NaOH plus SO3. Okay, so that can make it into Na2SO4 plus H2. So this is reaction 1. The other reaction is 2 moles of NaOH plus H2SO4. That together can form Na2SO4 plus H2 plus 2H2. These are the two reactions that can be made. And now you can see for every 1 mole we require 2 moles of NaOH. So that means whatever be the number of moles of NaOH total, that total has to be twice the number of moles of SO3 plus number of moles of H2SO4 in bracket, right? These are the total number of moles required. So try to figure out how much is the number of moles of SO3 and number of moles of H2SO4 present in 178 grams of oleum. You note that while labeling, this part specially represent the amount of water that need to be added. So let us just put that into picture here. So that is 18. How do we write down that? 18 by 80, 18 by 80 into weight of SO3. That is equal to the weight of H2O that needs to be added, which is 900 divided by 89 given. So as you solve it, you can see weight of SO3. Weight of SO3 will be equal to 900 times of 80 by 89 times of 18. Okay. Let me put this as equation 1 here. This is when you have 100 grams of oleum. In 100 grams of oleum, this much amount of weight of SO3 will be present. So if 100 grams of oleum contains 900 into 80 by 89, sorry, by 80 into 89, 89 into 18 grams of SO3, then 178 grams of oleum must have how much? So that implies weight of SO3 is equal to 900 times of 80 multiplied by 178 divided by 89 into 18. This is the weight of SO3 that must be present in 178 grams of oleum. Okay. So solving this, you can see this is coming out to be exactly again 80 grams. Clear. So this is coming out to be 80 grams. Since this is 80, so weight of H2SO4 will be simply equal to 178 minus 80. Okay. So this is equal to 98 grams. So which implies weight of SO3 is 80 grams, which means number of moles of SO3 is 1 mole. Weight of H2SO4 is 98 grams, which means number of moles of H2SO4 is 1 mole, which means total number of moles SO3 is 1, H2SO4 is 1. So number of moles of NaOH required will be equal to 2 times of weight number of moles of SO3 plus this one. So that makes it 4 moles. Hence, 4 moles of NaOH is required. Got it? Please do check, everybody. This was a previous year question, previous year JE question. So please do check. If you have any doubt, let me know.
सर इन दैट WSO3 वो एक बाय 100 भी होगा ना 178 ग्राम वॉल्यूम के लिए
हाँ, into 100. Finished, everybody? Is it done? See, the next topic is about identifying what is degree of hardness of water. Okay. See, hardness means it does not, if a water is not able to give the lathering, due to soap. So if a water is free from soluble salts of calcium and magnesium, then we call it as a soft water. Okay. So if it comes to lathering, the soft water can easily give lathering, but the hard water becomes little difficult. Okay. Why is that so? Mainly, soft water contains the dissolved form. Soft water mainly contains, sorry, soap mainly contains C17H35 CO minus Na plus sodium stearate. Okay, this is the main ingredient.
Can you repeat the name?
Sodium stearate. Okay.
Yes, sir.
Now, what happens is when it comes to hard water, this sodium stearate will form a precipitate with calcium and magnesium dissolved ions. So its ability to start forming lather decreases. Got it? And this is the reaction that would happen. Let me just put down that reaction here. That is C17H35 COO minus plus calcium 2 plus. That converts into C17H35 COO twice calcium. The same logic applies with magnesium also. Okay. So that plus 2 moles of Na plus, if at all I write the Na plus here itself. All right. Now our objective should be to somehow remove out this calcium or somehow remove out this magnesium. Got it? So if you are able to remove that out, precipitate it out, clear, from the water before we add the soap, then that means you are dealing with now soft water. Got it? So check out how do we remove the hardness of water so that we can make it softer to use it more easily. Okay. There are several methods. Broad way, there are two methods: temporary hardness and permanent hardness. Basically, the hardness itself is of these two types, and these two types can be removed out with simple methods sometimes more chemically oriented methods. Temporary hardness is about removal of bicarbonate and dissolved salts of magnesium and calcium 2 plus. So that means if magnesium and calcium are dissolved in the form of bicarbonate in water, and if you are able to remove that, that means you are trying to remove the temporary hardness. Okay. And now, how do we do that? We can use a simple method, as you can see, by boiling. Okay. Simply by boiling it, we will be able to make the dissolved form of calcium bicarbonate and magnesium bicarbonate into carbonate precipitates. Okay. See, on boiling calcium bicarbonate or magnesium bicarbonate, both will get easily precipitated here. Okay. Got it. So that's one way to remove the uh, calcium form. Now, second thing is by adding Na2CO3. Okay. Second thing is by adding Na2CO3.
So there's some
Now,
obstruction on the screen. Now,
now it's gone, I guess. Yeah. Yeah, that was your chat window. Once. Calcium bicarbonate plus Na2CO3, that will convert into calcium carbonate and 2 moles of sodium bicarbonate. And now the sodium bicarbonate part is soluble while calcium will get precipitated here. Okay. Basically, if you increase the concentration of CO3 2 minus, that calcium 2 plus will react with that CO3 minus to precipitate into CaCO3. Magnesium bicarbonate will also precipitate, but this time magnesium carbonate and magnesium bicarbonate both will get precipitated, giving more composition of magnesium bicarbonate. See, the solubility of any salt is decided on the basis of something called their Ksp value. Okay, Ksp represents how much amount of salt will get dissolved when it is in a solid form. For example, if you notice MgCO3, if you take a solid, put it in the aqueous solution, that means you have kept infinite amount of water, sufficient amount of water, in which a small composition of magnesium ions and small composition of carbonate ions will be present. Majority of the part will be existing in MgCO3 only. So the product of these two compositions, that is Mg2 plus and CO3 2 minus, this is called solubility product. It is a constant value. For every salt at a room temperature, it will have a constant value. Agreed? So the product of Mg2 plus and CO3 2 minus remains constant. And that constant value is what is called as Ksp. So the best way to judge like
explain again.
which of the salts are soluble or not is to check their Ksp value. All right. Pardon, Vita. Want me to discuss
So
again?
can you repeat what KSP is?
Yeah. Ksp is called the solubility product. Okay. Constant of solubility product. What does that mean? It is about how much the salt is going to get dissolved from the solid part. सिंपल से एग्जांपल ऐसे लेते हैं, आपने चॉक पीस लिया, पानी में डाला. ओके. क्या चॉक पीस पूरा डिसॉल्व हो जाता है क्या? नहीं ना. बहुत ही छोटा अमाउंट चॉक पीस का आयंस में डिसॉल्व होता है. बाकी सारा तो सॉलिड फॉर्म में वैसे ही रहेगा ना.
Yes, sir.
ओके. So majority of the part will remain insoluble. An extremely small part will get dissolved. That's why Ksp values will be in the range of usually -10, -20, -30, -50 like that. Okay. Now, if if you notice MgOH twice versus MgCO3, the Ksp value of MgCO3 is slightly more than Ksp value of MgOH twice. What does that mean? That means given the chance, out of these two, which one has more ability to precipitate? The one which has lower Ksp value. Remember, जिसका भी Ksp वैल्यू कम होगा, that means that has more chances to get precipitated. Clear? So it is like a scale by which you can compare two salts, like which one is going to be more soluble or less soluble. For instance, NaCl का Ksp बहुत high है. What does that mean? That means most of the NaCl solid, common salt, when you add it to water, it get dissolved. Clear, beta? Of course, there is a saturation point even for NaCl also. There will be a saturation point after which you cannot further dissolve NaCl as well. Got it? But that saturation point comes after a huge solubility or huge amount of salt getting dissolved in water. Ishman, is that clear, bacha?
Yes.
Fine. Okay. So normally what you notice is magnesium hydroxide has a lesser Ksp value than MgCO3. So chances are this will get more precipitated, this will get less precipitated. Now, whether this will get precipitated or not, that also depends upon how much carbonate ion you are adding. More the amount of carbonate you add, more is the precipitation you can get. Okay. Clear on this point? Right. Now, this method of using Na2CO3, or you can use another term which I forgot to write. Everybody, please make sure that you write it in the notes. Calcium bicarbonate. If you are directly reacting with NaOH or CaOH twice, specifically in NCERT it is given as calcium hydroxide, and then boil it off. So we will get CaCO3 in an insoluble form plus 2H2O. Okay. Now this method of removing bicarbonates by adding calcium hydroxide, this is called Clark's method. Clark's method. Okay. So by chance if this terminology is used, remember it means you are trying to add calcium hydroxide. Okay. Yeah. Next, what is permanent hardness? Permanent hardness is mainly caused because of the dissolved salts of chloride and sulfates of calcium and magnesium salts. Okay. Here we have chlorides and sulfates of magnesium salts. Now, this can also be removed out more easily. Okay. So let me just add here at the end, how we can do that. One second. Yeah, here I'll put it as a note. Okay. What does that mean? See, CaCl2 is there. I can directly use Na2CO3, correct, to convert that into CaCO3 plus NaCl. NaCl is always in a dissolved form, so there is no problem. This is one way of removing out calcium. Even if you have calcium sulfate also, you react that with Na2CO3, it will convert into calcium carbonate, and Na2SO4 is a dissolved form. Okay. See, these chlorides and sulfates, when they are in a dissolved form, that is not going to cause any problem to the water. Okay. The water will remain still soft only. It is the problem with the calcium 2 plus ions and magnesium 2 plus ions. Got it? Clear, beta? Other than that, is these are these to the only way we can do it? See, these are the same equations valid even for magnesium also. Okay. But there are several methods. Okay. The other one is permutate method. Permutate method. Okay. Permutate method is basically you will be adding hydrates of silicates, hydrated silicates of aluminum and sodium. This is called as zeolite or sodium zeolite. See, sodium Sodium zeolites are being added. Okay. What are sodium zeolites? Na2, Al2, Si2O8 dot XH2O. This is the formula for a zeolite. Okay. For our understanding, we can write this as Na2Z. Na2Z. Got it? So, what exactly we do? Na2Z plus calcium 2 plus present in water, that will form CaZ plus 2 moles of Na plus. 2 moles of Na plus. Okay. This is the way we can remove out the calcium, and the same logic applies to magnesium also. Okay. Have you heard about filtering candles? For water filter, if you notice, okay, nowadays RO is more preferable, but uh, before RO, in fact, a lot of lot of water filters still use that. You would have, of a filtering rod. Basically, the hard water is being poured from the top, and you will get soft water from the bottom. Okay, got it. So here, this entire candle, this is this entire thing is called as candle. Okay, filtering candle. That candle basically consists of uh, zeolite. So zeolite will absorb all the calcium and remove rest of the part. Clear, everybody? Now, if you, I'm sure you may not have experienced this, at least, but my generation have always, I mean, this is one of the things my moms will all, our age moms will always tell us that whenever the water is not coming properly out of the filter, they'll say change the candles. Okay. So we used to go to a shop. There used to be typically shops for this. Got it? So we used to give these old candles and take the new candles. Got it? And we just used to bring it up and fix it on the fix it with the screw. That's it. Got it? So basically, these old candles, when we exchange with the dealer, what they will do, this calcium 2, which is present, right? That they will add with, high concentrated salt. Got it? They'll mix with high concentrated salt. So what happens? Slowly, the calcium will start replacing it and removing calcium into soluble form, and again regenerate your candles. Okay. So this is called regeneration of permutate. Clear? So this way it was useful, the candles were useful for a very long time. Okay, right. The last one is Calgon, Calgon method. Calgon method. Okay, literally translates to calcium gone. Okay, calgon. Okay, so that means you are removing the calcium out of it. Remember it that way. Okay, this is Calgon. So Calgon method is adding a complex salt of metaphosphoric acid. Got it? HPO3. HPO3 is called metaphosphoric acid, and the complex of that means you're adding with some base and making into a salt. That salt is called as metaphosphoric acid, sorry, salt of metaphosphoric acid. And what is that salt we are taking? Is this one, sodium hexametaphosphate, that is Na4PO3 6 times. Hexa, sodium hexametaphosphate. Got it? So its structure is actually like this: Na2 outside, right? And another Na4, another Na2 inside with phosphate, PO4, sorry, PO3, 6 times like this. Okay. And this, when you treat with calcium 2 plus ions, okay, calcium 2 plus ions, then calcium will start precipitating with it. So that is calcium Na2, okay, sorry, Na2 outside, Na2 outside, the calcium inside will get precipitated with this phosphate like this. Now this is a precipitate, and what do we get is 2 moles of Na plus out. Okay, so this got precipitated, calcium has gone, and Na plus has been removed out. Okay, calgon is mainly used when the water is very hard, correct? Especially due to permanent hardness, like sulfates. High concentration of sulfates are there, correct? In that case, this is mostly used. Okay. Lot of time you will have something like water softeners. Okay, nowadays we add something called fabric softeners also, correct? So if you notice, washing powders, right, Ariel washing, Surf Excel, all of these kind, they would always have some softener added into it. Got it? Of course, it is hardly noticeable considering we always use water from the municipality. Okay, but if you have to use it in the villages, there is high concentration of Ariel or you know Surf Excel, and these kind of washing powders are used because we require lot amount of salt to remove the existing calcium 2 plus, which is high in concentration. Clear, everybody? Right. So these are few methods by which you can remove permanent hardness. These two are mainly used to remove the permanent hardness. Okay. Right. There is one more method called ion exchange method, but that we will study it separately as a part of hydrogen chapter. Okay, that I haven't discussed. That's why I'm not discussing that part here. Got it? Now notice what is degree of uh, degree of hardness. Okay, to understand the degree of hardness, check out how do we measure it. The amount of calcium carbonate or the equivalent of calcium carbonate that is present in the solution in ppm units is called as degree of hardness. Got it? Understood? What does this mean? Suppose no matter in whatever the calcium salt form it is or magnesium salt form it is, you convert that form into calcium carbonate equivalents. Okay, let me show you with example. I think you will understand that better with examples. Check. Suppose if I gave you 100 grams of calcium carbonate present in 100 liters of water, what is the degree of hardness? Okay, as much as the hardness of water is calculated, we always assume one thing, that density of water aqueous solution is 1 gram per ml. That ain't changing. Okay, so which means since the density is 1, the volume and weight will be equivalent. So therefore, I can assume it like weight of H2O, solution. I mean, aqueous solution here, I'll simply write it as H2O. That is 100, kgs. 100 liters is similar to that of 100 kgs. And weight of uh, calcium carbonate that you're adding is 100 grams. Got it? So therefore, what will be the degree of hardness? See, degree of hardness is defined as how much is the weight of calcium carbonate which is present in the given weight of H2O. Okay, that into 10 raised to power of 6. That 6 represents that you are doing this in parts per million. Okay, so weight here is 100 grams divided by This is 100 into 10 raised to power of 3 grams into 10 raised to power of 6 grams. Make sense? Clear? So you can see the 5 will get cancelled. So what do I get? 1000. So 1000 ppm. So that represents the degree of hardness. Everybody, by definition, I think it is clear that what exactly is degree of hardness. Now look into this question. Suppose if it is been asked 111 grams of calcium chloride, 95 grams of magnesium chloride and 50 grams of calcium carbonate. See, degree of hydrolysis, degree of hardness is about converting every part of salt which is causing hardness into the measurable calcium carbonate. What does that mean? See, if you have 111 grams of calcium chloride, okay, first write that in number of moles of calcium chloride. So weight divided by molar mass. Molar mass is also 111. So that makes it 1 mole. Okay. Similarly, 95 grams of magnesium chloride. That implies number of moles of magnesium chloride is equal to 95 by 95. This is also 1 mole. Okay. Now 50 grams of calcium carbonate. That implies number of moles of calcium carbonate is equal to 50 by 100. Molar mass of calcium carbonate is 100. Okay. So that makes it 0.5 moles. Got it? Now, and try to understand this one. If 1 mole of calcium chloride is providing some hardness, right? Then calcium carbonate of 1 mole will also provide the same amount of hardness. Is this logic clear, everyone? That is, whatever the hardness calcium chloride causes, n moles of calcium chloride causes, the same effect will be observed with n moles of calcium carbonate. Because it is to do with the amount of calcium 2 plus ions. It has nothing to do with the form of uh, chloride or sulfate or carbonate. Clear? So that's why we can say that the hardness cost is calcium carbonate equivalent. If we write down, that means how much equivalent of calcium carbonate in total is giving the effect. I can say 2.5 moles. Is everybody understood this point? So therefore, weight of calcium carbonate equivalent, of all the hardness causing salts included together will be 2.5 into 100. Okay. So how much it is? 250 grams. So 250 grams of calcium carbonate. Okay, ऐसे समझो 250 grams of calcium carbonate अगर आपने लिया है और जिसकी वजह से जो भी हार्डनेस हो रहा है, that would be same as causing by 111 of calcium chloride plus 95 plus 50 grams of calcium carbonate. Clear, beta? So since we got the weight, now what will be the degree of hardness? That is equal to weight of calcium carbonate by weight of solution. Solution is, water into 10 raised to power of 6. So this is the basic formula for degree of hardness. So therefore, degree of hardness is equal to 250 divided by weight of solution. Weight of solution is how much? 2000 liters. Okay. So 2000 liters means 2000 into 10 raised to power of 3. That into 10 raised to power of 6. Alright. So you could notice that the 6 would get cancelled here, right? And only 2 will be left. So 2 will be left means how much? 125 ppm. Got it? Typically, if you have 100 ppm and less, then we can assume it like more soft water. Right? That means calcium presence is very less. Okay, कि उसको almost soft की तरह use कर सकते हो. Okay, if you dig into ground, usually we always measure uh, groundwater, from wells. If you notice, that will have minimum of 300 to 3000, that much range of ppm of calcium, uh, I mean degree of hardness present. Okay, I guess all of you got this point, how to calculate degree of hardness. Okay, please first check out these two questions. If you have not noted down or not, then you have to do it the next. If anybody didn't get this, please do check. See, 20 milligrams of calcium 2 plus ions. When it is written it as calcium 2 plus, that means you should understand we are talking about the atomic mass of calcium 2 plus only. Okay, so which implies how many moles of calcium 2 plus are present here. So number of moles of calcium 2 plus implies what is the weight, right? That divided by molar mass. Calcium is 40. So that is 0.5 millimoles of calcium 2 plus. So if that means number of moles of calcium carbonate equivalent will be same as number of moles of calcium 2 plus, which is equal to 0.5 millimoles. Hence, degree of hardness will be equal to weight of calcium carbonate divided by weight of solution, aqueous solution, into 10 raised to power of 6. So 0.5 millimoles, that is 10 raised to power of minus 3, into weight of molar mass of calcium carbonate is 100, that divided by 1 liter. 1 liter is 10 raised to power of 3 grams. Okay, that into 10 raised to power of 6. This is what we are supposed to do. Clear? So how much we are getting? This is what we are getting it as 50 ppm. Then everyone, please check. See the next one. The next question is about calculate the mass of calcium oxide in kgs that is required to remove the hardness of 10 raised to power of 6 liters of water. Okay. See, calcium oxide plus calcium bicarbonate. Okay. That when you add it together will convert into 2 moles of calcium carbonate plus H2O. Got it? And now, how much is the weight of this one? 1.62 grams. Correct? And using this, you can first calculate number of moles of bicarbonate. So calcium bicarbonate, right? So that is equal to 0.01. Sorry, which is, I'll write it down clearly, 1.62 by 162. 162 is the molar mass. So it is 0.01 moles. 0.01 moles. Okay. So number of calcium oxide per liter is how much? 0.01 moles. Because you can see the mole ratio here, 1 is to 1. Okay. So if this many moles are present per 1 liter, so 10 raised to power of 6 liters will have how many moles? It will have 10 raised to power of 4 moles of calcium oxide. Okay. So therefore, weight of calcium oxide, you know, in kgs that you need to add will be equal to 10 raised to power of 4 into 56 is the molar mass into 10 raised to power of minus 3 if you are to write it in kgs. So that will be equal to 560 kgs. Okay, clear beta? So if you have 10 raised to power of 6 grams of water, correct? So this much amount of calcium oxide is added. Okay, usually this is what you will see it in reservoirs. Okay, reservoir standards are like this. Understood? So municipality, when they send water to us to use it in our, what we call it as the tap water, before that, that goes through lots of filtration processes. Okay, one of them is, the water that comes into the reservoir, you will add the desired amount of calcium salt. Right, Utsa? That's correct. Pratisha, right? Everyone understood this point? Right. Any doubt here? Now, let us understand what are double titrations. Okay. See, double titration is something which we'll be studying again and again. I mean, we will come across ionic equilibrium. There also we'll study. And here also, as a part of redox, we can study. All right. You can just give me a minute, but okay. Simple terms. An acid-based titration will always give you salt and water. Okay. So, but when you have an acid-based titration happening, we need to know at which point we need to stop. Okay. So that the end point or the equivalent point is being achieved. What is an end point or equivalent point? I told you that before. Okay. That is when both the equivalents of acid and base are equal. Okay. So in that case, suppose if at all we are titrating something like this, NaOH and Na2CO3 mixture that is being titrated with HCl. Then now the question that will be asked is how many moles of HCl that are required to titrate NaOH and Na2CO3. That is the first thing you need to understand. Second thing is to recognize that we are achieving that equivalence point. That means we are able to neutralize that base. We require some kind of a color change. And how would I get the color change here? I'll be using two indicators. Okay. There are mainly two indicators that we'll use in lab. One is methyl orange, the other one is phenolphthalein. Okay. This is called methyl orange. Okay. It is a weak organic base. Then we have phenolphthalein. Phenolphthalein. Okay. This is a weak organic acid. So one is a base form, one is an acid form. What it does is whenever whenever the methyl orange is being added to the solution, depending upon the pH, I'm not sure if you are clear of pH. Let me just give you in a simple term. pH is the measure of how much H plus ions are present in the solution. So pH is always measured as minus log of H plus ions. Okay. So in short, if the H plus ion concentration is more, the pH of the solution is less. Okay. In fact, if pH value of the aqueous solution is less than 7, we call it as an acidic solution. If it is greater than 7, we call it as a basic solution. And if it is equal to 7, we call it as a neutral solution. This is a typical norm in aqueous solutions. Clear? Now, this is the basic idea that you need to have. Suppose if your solution is, more acidic, that means the pH should be less than 7. Clear? Now notice within that acid also, if the pH of the solution is 3.3 and below, and if by chance you have added a methyl orange into it, then what is the color it will maintain? It will maintain reddish color. Okay. If it is acidic solution, but its pH is greater than 5, above 5, whether it is acid or base, the color of methyl orange will be yellow. Likewise, if the solution's pH is less than 7, less than 8, the color remains colorless if it is phenolphthalein. If it is greater than 10, the color will turn out to be pink. I hope this part is clear, everybody. Yeah. Now, individually, please check out what is the color that will be present in each one of them, as an individual solution. Suppose I have, only some dilute HCl solution. Dilute HCl maintains a pH of around 1 to 2. If it is 1 to 2, everybody tell me what is the color of methyl orange beta? It will remain red color. Correct? This is a table I would suggest all of you to practice along with me, okay? So methyl orange is red color. What about phenolphthalein? When pH is around 1 to 2, it will be colorless. Correct? If you take NaOH, NaOH is a strong base. Strong base will have pH close to 12 to 14. This is the range. Methyl orange, what is the color it will maintain? Yellow. Phenolphthalein, what is the color it will maintain? Pink. If you have sodium bicarbonate, and imagine I add 1 drop of methyl orange into it, okay? It is 8 to 8.5. 8 to 8.5 represent it is still yellow. While phenolphthalein, when it is present, what is the color? Just it is 8 to 8.5 is almost colorless only. So I can still take it as colorless or extremely pale pink. Next, Na2CO3 around 11 to 12. Again, this will remain yellow and phenolphthalein will remain pink. Got it. So all of you are clear? What is the pH? At what pH? What is the color? The indicators will provide. Now let us slowly come to this point. Imagine I'm titrating HCl and NaOH. Only these two are being titrated. Okay. At the equivalence point, right? What would happen? See, when HCl is titrated with NaOH, that means you are adding NaOH into it. Okay. Here, let me write down. Adding NaOH. Here, adding Na2CO3. Here, adding, okay, sorry, my mistake. Here we are adding HCl, adding HCl. Here also we are adding HCl, adding HCl. So we are adding HCl to the solution which has NaOH, Na2CO3 or NaHCO3. Okay. What should happen? pH should change, right? Originally, what is the pH when there is only NaOH? NaOH around there, it is 12 to 14. 12 to 14 means what is the color that will be indicating here? So this will be pink to colorless. Correct? This will become pink to colorless. Methyl orange, what is the color it will change? It will be yellow towards when all the HCl is been added. I mean, if HCl is been added excess, then it will start turning into red color. Then when it comes to Na2CO3, this will also be the same, pink towards colorless. Methyl orange will also be yellow towards red. NaCO3, if you notice, this is colorless only. Colorless remains colorless. Methyl orange will be yellow to red. Is this learning clear, everybody?
वो
During the
आपने क्या लिखा है
titration,
पिंक टू और HCl and NaOH.
that is colorless. Let me write fully. Okay? In these three cases, you should know how the color is changing with different indicators. Now, coming to this point, whenever we do titration of NaOH and Na2CO3 mixture with HCl, let's say, okay, then what are the chemical reactions that will happen? See, NaOH and Na2CO3, both of them are sufficiently strong, but NaOH is much stronger. So between these two, HCl will first mainly interact with NaOH. So imagine this is the first reaction that is happening. X moles of NaOH will require X moles of HCl to convert into salt and water, correct? Right, everybody? So therefore, X moles of HCl is required in titrating this one for NaOH. What about Na2CO3? Y moles are present. Now notice, Y moles require Y moles of HCl to convert into NaCO3. And NaCO3 can be further titrated with HCl to get NaCl plus H2O plus CO2, correct? Which means how many moles totally HCl is going to require to complete the titration of this one, to completely uh, react with all the amount of basic nature that they can provide. So NaOH, Na2CO3 totally how many moles of HCl is required? X plus 2Y. Does that make sense? Okay. Now imagine this, everybody. Okay. Listen to me carefully. Check out. Imagine you took NaOH and HCl in a test tube. Okay. Sorry, NaOH and Na2CO3. This mixture you took it in test tube. Okay. So this is the test tube which you took. In that you have this mixture which is NaOH and Na2CO3. Correct. So this is, let's say, very pale white color. I'll just write it this way. Okay. This is like pale white color. Right. So this is the colorless, almost colorless form which is present. Now to this, what you are doing, if at all you add, correct, phenolphthalein, if at all you add phenolphthalein, okay. Now what is the color do you think this will convert into? Okay. What is the color does it show? Phenolphthalein should start showing pink color, isn't it? Because this mixture, NaOH and Na2CO3, both of them are highly basic. So the pH of the solution would be around 12, 13 like that. So what is the color it will show? It will start showing pink color. Now this is the color of the solution you will have. Okay. And from the top in the burette, we would have HCl. This is burette. And here we have HCl. From HCl, you're titrating that. Clear? So during the course of titration, these are the three reactions you will notice. Okay. First, notice this. After adding X moles, see X moles of HCl has been added into it. After adding X moles of HCl, what happens? NaOH is getting consumed. NaOH is getting consumed. But do you think, everybody, do you think, will there be any color change? No, right? It will still remain pink. Why? Because because Na2CO3 is left. And with Na2CO3, if you go above and check, what did I tell you? With phenolphthalein, Na2CO3 will still give you pink color only. So, pink color does not disappear. Everybody understood? After adding X moles, the pink color is not disappeared yet. But after adding Y moles of HCl, another Y moles, first X moles and then the next Y moles. After adding that, what has happened to the phenolphthalein now? It has become colorless. Got it? Now, this part has become colorless after the titration. Clear? So after the titration, it has been colorless, which means how many moles that you must have added here? How many moles of HCl you must have added? X plus Y moles you must have added during the titration. Clear? Is this logic clear, everybody? Okay. So after X plus Y moles, you will stop the titration. See, the objective of the titration is color change hua rok do. Okay. So using phenolphthalein, how many moles of HCl you have actually added? You have added X plus Y moles. Okay. So do you think using phenolphthalein, can we do the complete titration of acid and base? No, you can't. You can only do up to formation of bicarbonate. Bicarbonate and HCl can never be recognized using phenolphthalein. Important. Bicarbonate and HCl reaction can never be recognized using phenolphthalein. Got it? Now let me put the same thing in an alternative way. This is for phenolphthalein form. Okay. So now let me elaborate the same thing with methyl orange. Okay. With methyl orange, what was the original color here? Okay. What could have been the original color here? Only this is the part I need to change. Okay. So here I am adding methyl orange. Imagine I added methyl orange, MEOH. So on adding methyl orange, what is the color you will notice inside? It will be yellow color, right? Solution will be yellow color, correct? And after the titration, what is the color we expect? The color we expect is red color. So it should become red color inside. This is what you expect in methyl orange, okay? Now tell me, everybody, notice this carefully. You are titrating NaOH and Na2CO3 ka mixture with HCl by using methyl orange as the uh, methyl orange as the indicator. Imagine this. First you added X moles of HCl, correct? Do you think color will change, beta? No, it will not change. Why? Because Na2CO3 is present and Na2CO3 will also represent yellow color only. Got it? After that, Na2CO3 will be further titrated with HCl because आप रोक नहीं रहे हो, because color change नहीं हो रहा है ना. Till the color change is not happening, you will keep on titrating. Okay. So X moles have been done. Now you have added Y moles also. Still it remains white, yellow. After Y moles, you will add another Y moles. Still it remains yellow. When from this Y moles, when you add extra 1 2 drops, then the color will start converting into red color. Clear? So that means you will immediately stop. You will subtract that volume of 1 2 drops and report it. This is what you will do it in lab also. I mean, this is first year lab, which you have to do it. Okay. So when you do titrations, this is one thing you will do. Whenever it is with methyl orange, correct? You'll always have to add that extra 1 2 drop so that everything will become red color. Got it? Now can I say something? The total moles that you have used here to titrate is X plus 2Y. Isn't it? Is this part clear, everybody? So with methyl orange, complete titration will happen. This one. This is with, you know, see here I have written. Using phenolphthalein, number of moles of HCl you will use is X plus Y. Using methyl orange, you will use X plus 2Y. Everyone, please let me know if you have any doubt in this titration. If you have understood this titration, I'll go to the next one. Right. See, as per the question, we have 25 ml of a mixed solution of Na2CO3 and NaHCO3 requiring 12 ml of 0.05 normal HCl when titrated using phenolphthalein as indicator. But when 25 ml of the same separate mixture is titrated with methyl orange, we require 30 ml of 0.05 normal HCl. Calculate the amount of Na2CO3 and NaHCO3 in gram per liter. That is in liter, how much grams of Na2CO3 is there and how much grams of NaHCO3 is there. Okay. Let us assume the moles of Na2CO3 are A and moles of NaHCO3 are B. Let us assume this case. Now, in using phenolphthalein, okay, using phenolphthalein, number of moles of HCl will be how many? How many moles will be using everybody? Only A moles, correct? And using methyl orange, how many moles of HCl you will be using everybody? Will be using 2A plus B. Any doubt in this part? Everybody understood why I have written that? If we assume this is A moles and this is B moles, using phenolphthalein, I can only recognize Na2CO3. NaHCO3 I can't recognize. And using methyl orange, I can recognize Na2CO3 and everything of NaHCO3 that is present. Now, what is it given? Number of moles of HCl given using phenolphthalein titration is how much? 12 ml into 0.05 normal. Acha, normality into molarity, how do we convert? Let me write on that first. You know that normality is always equal to molarity into valency factor. Okay. And valency factor of HCl is 1 because it is able to give only 1 H plus. So therefore 0.01, sorry, 0.05 molar molarity and normality are same. So molarity will also be equal to 0.05 molar. Okay. So from here, number of moles of HCl using phenolphthalein is how much? That is equal to 12 ml into 0.05 moles. This will be millimoles. So A we got it. A is equal to 12 into 0.05. Okay. These many millimoles. And what about B calculation here? Check out. Molarity, number of moles of HCl in this case will be equal to 30 into 0.05. Correct. So 2A plus B is equal to 30 into 0.05. Clear, everybody? Right. So how much we are getting here? So you can see here how many millimoles we have. 2.4 millimoles here. And what about here? 6 millimoles. Solving for A and B, you will get what is the value of A and what is the value of B here. Okay. Right. Everybody got that? That's correct. Sure, it's right. It's that's right, bacha. But surely that is in moles, na beta. You have to write it in grams.
Okay, sir, I'll solve it.
Hmm. Yeah. So make that's right. Okay. Check, everybody. So we got the number of moles. So what is the weight of uh, Na2CO3? Na2CO3. Okay. Na2CO3 is 46 plus 60. So 106. Molar mass is 106. So 2.4 into 106 into 10 raised to power of minus 3. These many grams are present in how many? 25 ml per 25 ml. Okay. So if 25 ml has this much, so 1 liter will have how much, beta? Okay, 25 ml has this much. So 2.4 into 106 by 25 into 1000. Okay. Now this 1000 into 10 raised to power of minus 3 will get cancelled. So this many gram per liter. Okay. So 2.4 into 106 divided by 25. This many gram per liter. This is the weight of Na2CO3. What about weight of NaHCO3? Okay. NaHCO3. Got it? So here first you calculate B. See, this is 4.8 plus B is equal to 6. So B is equal to 1.2 millimoles. Got it? So that is equal to, same logic here. The molar mass of NaCO3 is 84. So therefore 1.2 into 84 divided by 25 gram per liter. Clear? Everyone understood this point? Right. See the next question here. It's in a very similar terms. 20 ml of mixed solution of Na2CO3 and NaOH require this much of HCl when titrated with phenolphthalein. But when methyl orange was added, a second equivalence point was observed. Okay, that means a further 2.5 ml of HCl was used. Find the mass of Na2CO3 and NaOH in grams. We didn't take two different solutions. We took a same solution. First, we did titrate with phenolphthalein. Then we continued with methyl orange. Okay. Try it for a minute, then I'll discuss. Right. Notice this one. Using phenolphthalein, number of moles of HCl that we will be using is A plus B. Okay. And that must be equal to 17.5 into 0.1. Let us put this as equation 1. This is millimoles. Let us put this as equation 1. Okay. Now, using methyl orange. Methyl orange is only to titrate the rest of the amount of NaCO3. So the amount of HCl that is to be used is only A moles, because A moles of Na2CO3 produce A moles of NaCO3. So that should be equal to rest of the amount. So 2.5 into 0.1 millimoles. This is equation 2. Okay. So from here we can get A is equal to 0.25 millimoles and B is equal to 1.5 millimoles. Okay, if you subtract from there. So what will be the mass here? So the mass of Na2CO3 will be equal to A times of 106, 0.25 into 106 milligrams, and mass of NaOH will be equal to B times of 40. 40 is a molar mass. So 1.5 into 40 milligrams. This is what you should get. Okay. So this is coming out as 26.5 milligrams, while this is coming as 60 milligrams. If the question is asked in grams, just multiply that with 10 raised to minus 3. Right, Utsa, Anna, that's right, beta. Good. I guess all of you got this point. See, same titrations, if at all I do it with H2SO4, okay, the reaction type is same. There is no change in the reaction type. You know what is the reaction type here? See, what is the reactions here? So 2 moles of NaOH first will react with H2SO4, will give you Na2SO4 plus 2 moles of H2O. Second, if Na2CO3 is reacting, will be reacting with H2SO4, 2 moles here. That will first convert into 2 moles of NaHCO3 plus Na2SO4. And 2 moles of NaHCO3 will be reacting with H2SO4 to convert that into Na2CO3, Na2SO4 plus H2O plus CO2. Okay, got it? So 2 moles of this and 2 moles of this, like this. These are the reactions that will happen with H2SO4. The only difference between HCl and H2SO4 is that here it will be 2:1 ratio in all the equations. There it is always 1:1 ratio in all the equations. Okay, so tell me, using phenolphthalein, how many moles of H2SO4 to be used now? Because phenolphthalein will recognize this one and this one. So how much it should be? X by 2 moles and Y by 2 moles. Then, while when it comes to methyl orange, it has to be X by 2 moles plus Y by 2 moles plus Y by 2 moles plus Z by 2 moles. Correct? So that is equal to X by 2 plus Y plus Z by 2. These are the number of moles of H2SO4 used. Okay, this is number of moles of H2SO4 that is to be used for titration. Same way, second thing, if you have X and Z using H2SO4, how much it is to be? X by 2 using phenolphthalein and X by 2 plus Z by 2 using methyl orange. And lastly, if you have Y and Z with phenolphthalein, I'll be using Y by 2, and here I'll be using Y plus Z by 2. I'll be using Y plus Z by 2. Okay. Please see all these three cases, everybody. If there is any problem, we can